let's look now at what happens when you don't have a plane mirror, but you have a curved mirror. So on this one, concave and convex. This is a good time to explain what those mean. So the concave surface, think of it like a cave, right? That's why it's got that name. So on this left side of this mirror, you can see that it's kind of caved in, right? So that is the concave surface. The other surface, the one that bows out, is called the convex surface. Now, if we talk about making this mirror curved in such a way that it is a piece of a sphere, so it's a piece of a hollow sphere, then if I draw a normal vector at any point on this mirror, all those normal vectors, this will form a right angle, they all point back to the center. So the center point C. And this F equals R over 2, this distance is R. That radius always hits perpendicular to the mirror and goes straight back to the center. Now we want to look at what happens when light hits a concave mirror. So concave, you can see it doesn't look like it's curved very much, but you can see that the front surface of this mirror is curved in a bit. So if I bring the laser in and hit it right in the center, it looks exactly like the other mirror did, the plane mirror. But look what happens if I start going off center. See what's happening? As I come up here, so I'm still bringing the ray in horizontally, but now it looks at first like maybe the incident and reflected ray are different. But we knew before that with a plane mirror, the incident and reflected are always the same. That's actually still true here. It's just that this mirror is now, the top part of it is curved downward. So as we go up to the top, it tilts more and more down. As we go to the bottom, it tilts more and more up. And if you look out here where the reflected ray is coming, it starts out higher, it ends up lower. In here, it's kind of on the opposite side, and it looks like somewhere here in the middle, it's maybe not even moving. So we have another laser ray box that can actually provide 5 parallel beams. So that can help us see what's happening if you bring 5 beams in at the same time. You can see they all come together at one point, okay? That one point, that's called the focal point. And so this distance from here to here, from the surface of the mirror to that point, is called the focal point F. So that's the small f for a concave mirror. Now the center of this mirror, okay, so a normal vector, if I look at this top one, the normal vector is somewhere here between those two. So it comes out this direction, hitting somewhere out here maybe. And then the line straight through the middle comes straight back here. The normal vector for the bottom one here is also about there, points somewhere about here. So that means all the normal vectors from this mirror end up somewhere here. All the rays meet here when they come in parallel. And if you look, this distance is about the same as that distance. So the distance, the focal distance, is actually half of that distance to the center of the mirror. So this is, the radius is here, focal distance is there, and that's where that equation comes from, that the focal distance is R over 2, because this distance, that was F, and then the distance out to here, that was R. So this is for a concave mirror. Now this time let's look at a convex mirror. So on this one, we've got the mirrored surface here, and you can see it's curved in a way that it's bulging out. And again, I bring the laser in, hit it right there in the middle, and it looks exactly like the plane mirror, it looks exactly like the concave mirror when you hit it straight on right in the center. But again, if I move off center, now you can see it's definitely not hitting straight the same way. So the incident light comes in, comes off that way. That means that the normal vector here is pointed right there in between the two, so that the incident and the reflected angle are the same. So this direction right here is the normal. And then as I come down, same thing, normal direction is right here. Okay, so the center of this curve is not actually out here in front of the mirror somewhere. It is somewhere back in behind here. So the radius is somewhere back on this side of the sphere. And if we bring in the 5 beams, you can see that for this one, all of the beams point to the same place, maybe somewhere right around here. So the focal point of this lens is actually back here behind the surface of the lens, or the surface of the mirror. Now normally it would be measured from the front edge of the mirror, so I didn't draw it very well there. So F in this case is right there. So where all those beams come together. And then if we drew all the normal vectors to come back, they would come back to someplace over here. So the radius R is there. You can see again that the F is shorter than the R, and actually it's the same thing again. That F is R over 2.